Hi, this is Hyungjin, and today I chose time series decomposition as a main topic for my presentation. Especially I'll cover the very classic models, which are additive and multiplicative, which Youngdong already introduced to you guys. So since I've just started to study time series, I might get lost a lot while explaining the content. So please excuse for that. Yeah, I'm kind of nervous right now, but yeah, let's get started. Before we move on to the models, I just want to define what decomposition means. So there is one approach to time series analysis is based on smoothing past data in order to separate the underlying patterns in the data series from randomness. These underlying patterns can be projected into the future and used as the forecast. Also, it can be broken down into sub-patterns to identify the components factors. Simply speaking, this procedure, breaking down series into different components, is called decomposition. Oh, yeah. In the last slide, I mentioned that decomposition is a procedure which aims to identify components of underlying patterns in data. The terms to explain each components may differ from person to person, but in a broad sense, these components are the main consideration. So the classical decomposition model. So there are two types of components. One is systematic, which have consistency or recurrence and can be described and modeled. In more detailed, level means the average value in the series, and trend explain the increasing or decreasing values in the series. The last one, seasonality, is about repeating short-term cycle in the series. The other one is non-systematic, which obviously means the opposite of systematic. The irregular components such as noise is included in this one. In a nutshell, we can say that a series is a combination of these components from this point of view. And this is this one is the formula for the classical model. So the only thing we consider for explaining the data at period t, which is on this yt parts, are trend cycle. It shows in TT and seasonal and noise vectors. It is quite simple. So, and yeah. So actually, there is one major assumption to describe the classical models, that the seasonal components is constant from year to year. Basically, is assumed that the same pattern will be repeated every year. Then what is the difference between additive and multiplicative model? As you can tell from their names, it is all about how to combine these factors. So additive adds up all the components like this one, this part, and multiplicative multiply all the components like this one. So I'll cover the additive decomposition first and move on to the multiplication models. So additive model argues that time series data is a function of a sum of its components. So it is appropriate if the magnitude, like the amplitude of the seasonal fluctuate, does not vary with the level of series. So let's take a look at the calculation process step by step. So the first thing we do is computing trend cycle using moving average. So moving average literally measure the average of observation while moving a window of a certain size. For example, MA with order 5 at time t is the average of observation in the preceding 2 period and observation at the time t and the observation in the following 2 period. So in this way, randomness of individual observation can be alleviated to drive an overall trend, like a more smoother trend like this. So the size of the order is determined according to the period set in the time series. For example, we'll set 7 for weekly data or like 4 for quarterly data. So however, if the period is an even number, like quarterly data, a problem occurs in that number of data because the number of data before and after time t is different in the window. So this can be prevented by multiplying the two to the MA formula. Since the formula behind this equation is so complicated that I'm not going to cover it right now, but all we need to know is that it is derived in this way to keep the influence of the previous and subsequent data within the window symmetrical. And if any of you guys want to know the equation, please check out the references that I listed at the end. So yeah, let's move on to the next step. So the next step is to calculate the trend series by subtracting trend cycle from the data, like this one. This one, it would be the data point at the period t, and the trend is tt. So we kind of subtracting this data, and that's the detrended series. So, and the next one, the estimate the seasonal component using these detrended series. For instance, if seasonality is derived for each month, the detrended value for each month are collected and averaged. So it's kind of simple, but and we have to, like, since the seasonality of each cycle represent an increase or decrease related to the trend, so it kind of showed how the trend is like fluctuate in the level of series. So we have to like adjust the sum of value to be 0. It is more like a normalizing things. So after that, we can calculate the remainder, the noise one, by subtracting trend and seasonal components. This remainder refer to data that are not captured within the regularity of models, which allows us to gauge whether this model is suitable for capturing the patterns in the data. So let's move on to the multiplicative one. So rather than a sum, the multiplicative decomposition argues that time series data is a function of the product of its components. So it's being frequently used if the amplitude of the seasonality is proportionally increasing or decreasing to the level of series, like fluctuate a lot. Pattern becomes like wider as time goes by. So therefore, this model is believed to be more appropriate for economic series than additive models. So the basic styles is similar to additive model. So let's move on to the image that which shows how these models work. So as you can see, this in this seasonal one, the classical model replicate the sequence of each period of the seasonal component, and it kind of duplicated by the end of things. So since it assumed that seasonal component is consistent each period. So yeah. Since these classical models are very simple, they have various problems. First, the estimate of the trend is unavailable for the first few and last few observations. So as I mentioned before, we have to average with a fixed number of observation before and after the period T while using MA. But the first observation does not yield MA since there is no preceding observations, and also that could be applied to the last one. So, but so also that means that there is no estimate of the remainder components for the same time period since we don't have any trends in the first or in the last one. So second, the trend cycle estimate trends to over smooth because we kind of average everything on the slide on the data. The rapid rise and falls in the data can be like removed so that it could cause a large remainder components like this one. There is a lot of remainders inside these models. So that could be one of the problems of these simple classical models. So last but not least, the basic assumption that seasonal component is constant throughout the entire series might not be suitable for longer periods because we can have any like variables can be affected to this trend. So to resolve these issues, various models like X11 or STL, etc., have been devised, and many people recommend to use these alternative models these days. So nevertheless, since this classical model that I introduced are the most basic model, I think understanding their mechanism might help us to understand other state-of-art model as well. So that's all I have for today. These are the references that I found, and there are many other things that are not covered in today's presentation. So if there anyone interested in this topic, please check out this link. And thank you for listening. Yeah.